All right, hello everybody. Going to be taking a look at a couple guided examples dealing with two-dimensional collisions. So a few people expressed that they were having some trouble with the very last example in the content posted yesterday. So I'm going to start with that question, and then I'm going to also do a 2D collision where we have an inelastic collision. So we have two things coming in different directions and hitting together, and then what happens to them. So let's take a look at this problem from the notes. Okay, so a marble with a velocity of 1.6 meters per second hits a stationary marble. Okay, so VA is 1.6 and VB is 0. Each marble goes off at a 45-degree angle from the original path of the marble. Okay, so one hits and then they both shoot off. The marbles have a mass of m. So the mass of the first marble is the same as the mass of the second marble. Okay, so that's going to be nice. We're going to be able to cancel out mass from our equations because of this point. What are the speeds of the two marbles after collision? Okay, so we're trying to find VA prime and VB prime. So we don't know how fast it's going at the end. Okay, so we have a marble that is rolling along, hits another marble, veers off at a 45-degree angle, and the other marble does the same. Okay, so this is the pattern. They hit and they both break off into 45-degree angles. Okay. Now we don't get a direction here, but to make our lives easier, we can just make an assumption. So all we know is that it hits and it splits in the direction. Okay, and it's asking for the speeds of the two marbles, so it doesn't even care about the final directions of them. So to make things easier, we'll just pick a direction that our initial marble was going in and then base our calculations around that. So what I'm going to do is I'm just going to say this is headed east. Okay, so I'll just make myself a little compass to remind myself of what directions I want to be positive and negative. Okay. So I'm going to say the initial one's going east. So we have a 2D collision problem. Anytime we're dealing with two dimensions, we always need to split things into x and y. Okay. So I'll start with the x side. Okay. So we weren't told anything about it being perfectly elastic or perfectly inelastic, so we have to just stick with the normal conservation of momentum equations. We don't get to use anything else here. So right away, right, because the masses are the same, right, all of these have a single mass term, we can cancel them out. Now, normally we have things that are different masses, so we can't do that, but because all of the masses are the same here, we can get rid of all of them. Okay. In addition to that, the VB initially was not moving in the x direction. So it's stationary, so it has no velocity, so it has no momentum. So now we can kind of fill this in a little bit. So VAX, well, that's 1.6. VAX prime, so if you remember how we split vectors into components, okay, we're going to do that here, right? So VAX, okay, is going to be VA prime cos of 45, and VBX is going to be VB prime cos 45 as well. Okay. Now this is a positive between these two because they are both headed in the same direction, right? They're both going east in the x direction. And unfortunately, this is as far as we can go in the x. We have two variables, so there's no way to solve it from here. So we're going to have to take it over to the y side and do something similar. So we're going to make a conservation of momentum equation for the y side of things. Now here we have one goes up, one goes down. So one bumps up to the north, one bumps up to the south. So what that means is these have opposite signs. So I'm actually going to put a minus in here, okay, to represent that one of them is bouncing up and one of them is bouncing down. Okay. Just like before, right? All of the masses we can cancel out. Okay. And there is some other stuff we can cancel out too, right? VB wasn't moving, so it's a 0. There's no momentum there. And VAY is actually also 0. This is because initially it had a velocity, but that velocity was straight horizontal, meaning it didn't have any vertical component to its velocity, so it doesn't have any vertical component to its momentum either. Okay, so what that means is we get 0 equals VA prime Y, so that would be VA prime sine 45 minus VB prime sine 45. Okay. So we're breaking it into components as well, because the goal is to find VA prime and VB prime. So we don't want VAY, we just want VA prime. Okay, so we can rearrange this equation. We can get VA prime sine 45 equals VB prime sine 45. Okay, we can divide out sine 45, and we're left with VA prime equals VB prime. So because these things are the same mass and they break off at the same angle, we end up finding that they are moving at the same speed afterwards. Okay, so now we can take the fact that we know this and we can put that into the other equation here. So 1.6 equals VA prime cos 45 plus VA prime cos 45. Now we only have one variable. Really easy to solve from here. So 1.6 equals 2 VA prime cos 45. So VA prime is 1.6 over 2 cos 45. So we run that through our calculator. Okay. And we get a final answer of 1.1 meters per second. So what that means is both, because they're the same, the final speed of each marble is 1.1 meters per second. Okay, and that's the answer that was posted in the notes, but this kind of shows you how to get there. So important things to be aware of in this versus normal, a normal conservation momentum problem, is we have to split it into X and Y. And there will be times where something will have a momentum in the X, but will not still have momentum in the Y direction, right? So VA was traveling in one direction. We made it east, okay? And so it had an X direction, had X momentum, but because it wasn't moving in the Y direction, on the Y side of things, it started out as a 0. So that's kind of the trick to solving this problem. Okay. Let's take a look at another one where we have, we're going to take a look at another one here. This time we have two separate objects that are going to have a collision and they're going to stick together. So two automobiles collide at an intersection. The mass of one car is 1,400 kilograms, and it is initially traveling at 12.5 meters per second south. And we have a second car with mass 1,300 kilograms traveling at 10.8 meters per second east. Okay. This time, things are going south and east, so I'm going to make those values positive. Okay. If the cars have a completely inelastic collision, what is their velocity just after the collision? So we're looking for V prime. And V prime, we know it's just one thing we're looking for because it's completely inelastic. That means the two things stick together and travel as a single object. So one is traveling east, one is traveling south. They're going to hit, and then they're going to go somewhere in the southeast direction. So we need to figure out what that is. So to do that, we are going to look at the problem through the x and the y, and then we'll have to put some things together. Okay? So let's start with x. Okay, so we have MA VAX, MB VBX, and we're going to have MA plus MB V prime, right? I'm just going to save some space, just put those together, right? Because they have the same velocity. Now, we can't cross out mass in this case because they're not the same anymore, but there are some things that we can zero out. So in the x direction, VA was traveling south, meaning it doesn't have any momentum in the x direction, only in the y direction. So we have 1300 times 10.8 equals 1400 plus 1300 V prime. Sorry, this should be V prime X, V prime X, V prime X. So with a little bit of simple math, we get 5.2 meters per second east. And that is the momentum it carries in the x direction. Okay? So now we need to figure out the y direction. So unlike in the last problem, here we were able to solve for everything we needed on one side. So what we're going to do here is we're going to find the x, we're going to find the y, and then we're going to have to assemble them into a complete vector. And once again, same setup. They have a combined speed because they stick together. Now this time, okay, VA had a vertical velocity, a velocity in the y direction, 12.5 meters per second going south. But VB was only going east. So what that means is, right, this value here is going to be 0 this time. So we've got 1400 times 12.5 equals 2700 VB prime. Sorry, not VB prime, VY prime. And we run that through our calculator. Okay, nice simple equation. 6.414815 meters per second going south. Okay. So now we have two vectors. We have Vy, V prime y, and we have V prime x. We need to find V prime. So we're going to do what we've been trained to do when we have two vectors, right? We're going to make a triangle, right? Vx prime, Vy prime, so that we can get V prime. Okay, so we're going to need to assemble these vectors using the Pythagorean theorem, and then we're going to need to use some trig to find the angle. Okay, so V prime is going to be 5.2 squared plus 6.4815 squared rooted. Okay. And that's going to give us approximately 8.3 meters per second. Okay, to find the angle, we're going to take the inverse tan of our two numbers, the inverse tan ratio of our two numbers, and we get an angle of approximately 51 degrees. So that means that after these two things collide, they're going to be traveling at 8.3 meters per second, 51 degrees, and I look at my picture here, south of east. So that shows how we can use two-dimensional vectors to solve a problem with perfectly inelastic collisions. Okay. So sometimes you're going to have to, rearrange equations and put one equation into the other, okay, which is the case that we had to do in question 1. Other times you are going to find Vx and Vy separately, and then you are going to assemble them into a vector to find. So always watch out for what clues the question gives. So here the question doesn't tell us that it's perfectly elastic or perfectly inelastic, so we just assume normal conservation of momentum. That's all we're allowed to deal with. Here, we're told it's completely inelastic, so we know they have a combined final speed. Okay. So that shows you how you can use these things to solve a problem like this. So hopefully that clears up two-dimensional collisions a little bit for everyone.